Hey, welcome back to Calculus. In this first of two lectures in section 6.2, we're going to take a look at how to use a definite integral to compute volumes of certain solids, namely solids where we can write down a formula for the cross-sectional area. Okay, so two objectives in this first part of this lecture. Here, I want to show you the kind of general principle of how you compute a volume by integrating cross-sectional area. So that's kind of the main idea. And then there's a certain kind of solid that has particularly nice cross-sections, volumes of revolution, solids of revolution, sometimes people call them. We're going to rotate regions in the plane about one of the two coordinate axes, the x or y axis. And then depending on what the region looks like and its relationship to those axes, our local estimates will either look like little disks or little washers. So sometimes people call these methods the disk method and the washer method. We'll just illustrate with examples as we go. All right, so to get started, let me tell you what a cylinder is. You're probably familiar with the word cylinder, and this picture in the middle is probably what you're thinking of when I say the word cylinder. That's a circular cylinder. So in mathematics, when somebody's talking about a solid being a cylinder, they don't necessarily mean that it's one of these circular cylinders. What they mean is it's a solid that cross sections parallel to its base are all the same shape. Okay, so at the base of this circular cylinder is a circle, and if I take cross sections parallel to that circle, they're all the same shape. They're all that same circle. So that's what makes that thing a cylinder. This rectangular box over here is also a cylinder in that sense. Its cross sections are all rectangles. Yeah, the cross sections parallel to the base are all rectangles congruent to the rectangle that's the base. This cylinder over here on the left, its cross sections, well, they almost look like little kind of parabolic pieces or something like that. But the idea is that at any level parallel to that base, the cross section is the same shape. So such a thing is called a cylinder. Okay, and the primary idea, the big point is that to calculate the volume of a cylinder, you take the area of the base and you multiply it by the height of the cylinder. All right, so that's the main idea of the volume of a cylinder is that here the area of the base is called A in this first picture. So the volume is that A times H. So if the area of the base is a circle, its area is, if the circle has radius r, its area is pi r squared. So the volume is that area times the height, right? The area of the base of this rectangular prism over here, this rectangular cylinder, is L times W. So L times W times the height is the volume. So that's the general principle, okay? Is that the volume of a cylinder is the area of its base times its height. How are we going to use that idea to form a local estimate for any solid? Well, if you take any solid region, you take a thin slice of it, it's approximately a cylinder. Yeah, if you cut some solid region into a bunch of thin slices, each slice, it won't be a perfect cylinder, but it's approximately a cylinder. So that's how we're going to try to take advantage of this idea. Let's continue. Here I've got, I took this picture from your book. So that kind of blue shaded thing is supposed to be this sort of irregular solid region. You're looking at it there. Maybe it's like a loaf of bread or something like that. And then the author is showing us that they're coordinatizing it. So for each x along some horizontal number line in this picture, for each value of x, if you take a cross section kind of perpendicular to that number line, yeah, that cross section. So think of it as slicing the solid with a plane perpendicular to the x-axis there, parallel to the y-axis. You slice that solid and it forms some region, right? It's shown there in what looks like kind of a purple color to me. And that region has some area, and you can see in this picture that that area varies depending on x, right? If we sliced this thing over here, this region doesn't have the same area as the one that's drawn in purple. Here the author is showing us the slice at the very end where x is equal to b. It's smaller than the purple area. So that area of the cross-section depends on x. So I'm just using function notation. I'm going to write a of x to denote the area of the cross-section of x. So the cross-sections are parallel and they're perpendicular to that x-axis. All right, and so the main problem is, well, how would we compute the volume of that solid if a of x isn't a constant? Yeah. If a of x is a constant, then the solid is a cylinder, and we would just take that constant value and multiply it by the length, which is b minus a in this case, and we'd get the volume. But here, a of x is changing as x changes. So we're going to use that principle I mentioned before. If you don't change x very much, then a little slice of that object looks like a cylinder, and we can use the principle. The volume of a cylinder is the area of its base times its height. So here on the left, I've got the same picture, except you can see you kind of have to maybe zoom in a little bit here. The author has thickened up the slice a little bit. So we're partitioning the interval from A to B. We're partitioning the interval from A to B, choosing a bunch of x values. It says xi minus 1, and that's xi. If you want to stop the video and kind of zoom in. And then what's this xi star? It's a sample point. It's a point chosen in the ith subinterval. All right. So that little slice here, this purple slice, it's not a perfect cylinder, but if delta x is very small, delta x is just the thickness, the width between xi and xi minus 1. If delta x is very small, then the volume of that little slice is approximately a cylinder. So I'm calling that our local estimate, right? That's our big idea in calculus, is that when things are not constant, if you look at a small section of them, if they're continuous, then they're approximately constant. So the volume of that slice, that purple region, would just be the area at, say, the sample point, xi star, times the thickness, because the thickness would be like the height of the cylindrical shell. It's the width in the orientation that we're looking at it. All right. So this one of these things is sort of this purple area, purple volume, pardon me, purple volume. Well, so if we do that for each one of the subintervals, in this picture, it looks like there's 7 or 8 of them, we would get these slices. It really does sort of look like a loaf of bread that you're slicing into slices. And each one of these slices, its volume is approximately equal to a quantity like that. So if we add all those up, I'm not decorating with all of the i's and putting in the indexes of summation. It's just sort of a schematic picture. Adding all of those up, remember we call that a Riemann sum. So the Riemann sum of those local estimates would give us an approximation for the volume of the whole solid. And then taking limits with respect to what? Well, taking limits as delta x goes to 0, right? As the thickness of the biggest slice goes to 0, then this Riemann sum will approach an integral. And that integral, well, it's going to be the integral of a of x dx. And what are the extreme values of x? Well, in the picture, they're a to b. So there's the first objective of the lecture, the volume of a solid whose cross-sectional area is given by some function of x. X is a variable on a number line perpendicular to the cross-sections, varying between a and b. You integrate that area with respect to x to get the volume. Okay, dimensionally, this formula can make sense because area, its units are square units, right? Square centimeters, square feet, square meters. dx is a one-dimensional measurement. It's a length, so its units would be like centimeters, feet, meters. And if you take square units and multiply them by units, you get cubic units. So dimensionally, this formula makes sense. If you have square feet times feet, that's cubic feet. That's the right unit on a volume. Cool. Let's take a look at an example. Let's state this pretty from the book. This is the definition that we're going to take. So if you take some solid region that lies between two numbers on a number line, like we were showing in the picture up there, and the cross-sectional area at x is given by some function a of x, then the volume of that thing is found by integrating. Taking the limit of those Riemann sums, you integrate the cross-sectional area with respect to x, okay? So that's the volume of that solid region. Okay, now let's look at an example. Let's use these ideas to show that the volume of a sphere with radius r is given by this, maybe it's a familiar formula to you, 4/3 pi r cubed. Okay, how are we going to use this? Well, a sphere has particularly nice cross sections. So if we place that sphere with its center at the origin, sort of putting its, one of its equatorial circles in the xy plane, putting its center at the origin, you see it in the diagram over there. And you can see in the diagram that I'm taking a slice at x. Where does x range between? X is ranging between minus the radius and positive the radius in this picture. So there's a slice at x, and I'm denoting by y that radius. That's the radius. This cross section is a circle, right? When you take a cross section of a sphere perpendicular to an axis like that, the geometric shape that you get is a circle. And that circle, I'm just naming its radius y. Okay, I can't call it r because r is the radius of the sphere. The sphere has already got a fixed radius. Okay, but we can determine what y is in terms of r and x, because in this right triangle right here, I'm going to just shade it in red for a second. The legs of that right triangle have length x, y, and r, and the Pythagorean theorem says that x squared plus y squared has to equal r squared, has to be the square of the hypotenuse. So algebraically solving that for y, I'm taking the positive square root because I'm thinking of y as that positive number as a radius. This is the radius of the sphere that we take the cross section x at x between minus r and r. All right, so since that cross section is a circle of radius y, we know what its area is. The area of a circle of radius y is pi y squared. But y is this square root of r squared minus x squared. So when you square it, well, you just get r squared minus x squared. So there's your cross-sectional area formula. This is the formula that we have to integrate from what to what? Well, we have to integrate it from minus r to r. So using that above notation, or sorry, that above idea, the volume of the sphere should be calculated by taking the integral of our cross-sectional area, that's our pi, times r squared minus x squared, times dx, and we integrate that from minus r to r over the extremes. All right. And to keep this video short, I'm not going to include all the calculation here, but I am going to use a property of integrals. Notice that I've doubled that integral, and I'm now integrating from 0 to r, not minus r. That's because this is an even function. R squared minus x squared times pi is an even function. So the integral of an even function over a symmetric interval, you can always calculate by 2 times the integral over half that interval. It simplifies the computation. All right, so I'm using some symmetry. If you like, what I'm saying is that if I computed the volume of half this sphere, so letting x go between just 0 and r, then doubling that would give me the volume of the whole sphere. That's basically the idea there. Okay, so here I've just kind of done the calculation and antiderivative for, remember, r is a constant. It's not specified, but it doesn't depend on x. So its antiderivative with r squared is just r squared x. The antiderivative of x squared is 1/3 x cubed, so I subtract them. Now I've evaluated, I plugged in x equals r, so I got r cubed minus 1/3 r cubed. Plugging in x equals 0 just gives you 0, so it's subtracting nothing. And then I've done the arithmetic, and you can check there. Yeah, 2 pi times 2/3 r cubed is in fact 4/3 pi r cubed. So there's the volume of a sphere derivation. Nice. You know, this sphere really is an example of a more general kind of object. If we think of this y equals the square root of r squared minus x squared as the graph of a function, I'm highlighting that function in red right now. The sphere is formed by taking the area below that function and rotating it around the x-axis, sweeping out a so-called volume of revolution. The cross-sectional area of a volume of revolution is a circle because we're, well, swinging something around an axis, and swinging something around an axis makes a circle by definition. All right, so we can kind of generalize that idea. That's what I'm going to do in this next slide. If you take any function f of x, and suppose, like in my picture, that it's greater than or equal to 0 for x between two numbers, a and b, and you let r be the region bounded by that function. Okay, so it's below the graph of y equals f of x, above y equals 0. The kind of region that you'd find the area of r by integrating f of x from a to b. But I'm going to form this so-called solid of revolution by rotating r around the x-axis. So can you visualize it in your mind? Think of that region R as being made out of some maybe piece of cardboard or something, and you're going to keep that cardboard attached to the x-axis, but you're going to swing it around and let this thing sweep out a solid region in space. So I'm not the greatest artist in the world, but I'm going to draw that region like this. So you can still see in my picture, yeah, I've got my region R, bounded by the x-axis and that graph of y equals f of x. And I've just rotated r around the x-axis. Sweeps out this thing. It kind of looks like a lampshade or something. And I'm calling that solid region S. And it's a solid of revolution by virtue of the way it was formed. And because we rotated everything around the x-axis, the cross-sections of it, this is the important part, the cross-sections at x are a circle, or people call it a disk in this business. I've drawn it in red there. This is a circle. Let me switch the pen color to keep it all. So a circle together with its interior is called a disk, right? And what's the area of it? Well, the area of a circle is pi times the square of its radius. The radius of that thing depends on x. It's precisely f of x, yeah? If you plug an x in there, the height of this point is the y-coordinate right there. Well, that's the point x comma f of x. It's on the graph of that function. So the area of the cross-sectional area of the area of the cross-section of the solid at x is pi times f of x squared. It's the area of a circle of radius f of x. All right, well, since the integral of the volume is the integral of cross-sectional area, if we just throw that into our integral formula, we get this disk formula. The volume of a solid of revolution for a function f of x continuous greater than or equal to 0 on a and b, r is the region bounded by its graph. The volume that you find is pi times the integral from a to b of that function f of x squared dx. And hopefully it makes sense. I brought the pi through the integral because it's a constant. It makes the formula look a little prettier. But that pi times f of x squared, that's the a of x. A of x times dx gives volume. Let's do an example. So I've got r, it's the region bounded by the function e to the minus x. Okay, I've drawn it there for you, a graph of e to the minus x over the interval from 0 to 1. It's greater than or equal to 0. I've shaded the region r here in the picture. It's shaded in gray. And I want to rotate r about the x-axis and find the volume of the solid. I'm showing you the solid S over here as a Mathematica generated graphic. So S is the solid region inside this little sort of bugle-shaped thing. And I'd like to know, what's the exact volume? What's the exact volume of S? Well, so we have all the right information. We're going to use this formula. It's brand new to us, but f of x is equal to e to the minus x. We're going to do this from 0 to 1. That's all we need to know. What are the x values for the limits of integration? What's the formula that's bounding the region? So let's compute this one. I don't have it written out this time. So the volume is using that brand new formula, the disk formula. It's the integral from 0 to 1 times pi of the function e to the minus x squared. All right, and now we're kind of in a Math 109 chapter 5 problem here. How are we going to compute that integral? Well, when you square e to the minus x, you get e to the minus 2x, right? And now what kind of technique are we going to, what kind of technique are we going to use to do that antiderivative, right? It's not just e to the x, but e to some function of x, right? But that function of x's derivative is a constant, so we should be making a u substitution there. So since this is kind of the beginning of our course, I'm going to put in some detail here to help you kind of remember how to do stuff like this. But I'm going to define u as negative 2x and then compute its derivative. All right, so du is negative 2 dx. And now I'm going to substitute that into my integral. I've got that pi out front. Instead of e to the minus 2x, I'm going to write e to the u. And then what's left to substitute in the integral? Well, I got to get rid of this dx. So I need to solve this equation for dx. Yeah, negative 1/2 du is equal to dx. So negative 1/2 is a constant. I'm going to put it out in front of the integral sign. And now I've accounted for everything. The integrals are equal, I mean, in terms of the indefinite integral, but I have to switch my limits of integration. right? Because u is equal to minus 2x, and these are x values. 0 and 1 are x values. So we have to do something like, well, when x is equal to 0, u is equal to negative 2 times it. So the lower limit of integration is still 0. But when x is equal to 1, then u is equal to negative 2 times 1. So the upper limit of integration becomes negative 2. Okay, so now we've switched our limits and now we can calculate the integral. I'm going to use another property of integration and write this as positive pi over 2 and then switch my limits of integration. So you can come to office hours if you want to kind of remind yourself of how to do some of this stuff. And now it's antiderivative time. So I've got minus pi over 2. The antiderivative of e to the u is itself. And I need to do that from negative 2 to 0. So that's pi over 2, putting in the upper limit, e to the 0 is 1, and then I subtract, putting in the lower limit, that's 1 over e squared, or e to the negative 2. All right, and I'll let you calculate this as a decimal if you want to. This is an exact value. So on like a quiz, if I was asked, or an exam, if I'm asking you for an exact value, this is the kind of form I want it in. I don't want a decimal approximation for it. And here, let me just to write something like units cubed to remind you that it's a volume. I didn't put units in the problem, but in the context of this thing, that's a volume. Cool. All right. Let's do another example. Same kind of thing. I've got a region R. I've drawn it there. It's the region between that line y equals x and y equals the parabola y equals x squared. And I want to rotate that region around the x-axis, but this one's a little different. This one's a little different because R is kind of bounded by two curves, neither one of which is the x-axis, right? So it's not quite the same, but we could kind of think along the lines like, imagine if we just ignored the red parabola for a second and rotated the graph y equals x around the x-axis. Can you visualize what it would be? It would make some cone, yeah? So what would the volume of that cone be? The volume of that cone would be pi times the integral from, well, we need to know where these things cross. You can see in the graph that that's x equals 1. Or you could solve the equation x is equal to x squared. It has two solutions, x equals 0 and x equals 1. So that's where these two curves cross. All right. So it could be the volume of the blue part. In fact, let me even write this in blue. If we take pi times the integral from 0 to 1, and then we take that function y equals x and square it, right? That's the volume that we would get from the blue curve. But that's not the right answer because we have to subtract from that the volume that we're going to get from, because our region is bounded below by this parabola y equals x squared. Yeah. So if you imagine what solid you'd get by revolving the region y equals x squared around that thing, it's kind of this, again, bugle-shaped thing. And we want to take that volume away. So I'm writing it in red. It's x to the fourth because it's x squared squared. So this is the desired volume. Yeah, the desired volume, you can think of it as a difference. It's a difference between two integrals. And because of properties of integrals, we can certainly write this as a single integral. And that's probably what I would do for computation purposes. Okay, so let's finish the computation here, just so we have it. So antiderivative, 1/3 x cubed minus 1/5 x to the fifth. And then we have to evaluate that from 0 to 1. So I'm not going to make this too laborious. You can ask me about it, but when you plug in 1, you'll get 1/3 minus 1/5. And when you plug in 0, you get 0. If you convert those to 15ths, you have to take 5/15ths, subtract 3/15ths, so you get 2/15ths. So 2 pi over 15 is the exact answer. It's the exact volume. that we're seeking. 2 pi over 15, again, cubic units. It's a volume. All right, but there's sort of another way to think about this. Instead of thinking about it as the difference of two volumes, it's kind of a nice idea to have, is that we could just make another local estimate. So another idea for the same problem. Let's make a local estimate. What do I mean by that? When I make a local estimate, I always choose some value of x. I'm going to choose a specific, a distinct color from what we're using here. So let me pick, say, an x value right there. And then I think about the points in my region that have that x value. Yeah, I just drew them in a little green line segment there. When I rotate r around the x-axis, what kind of shape is that green line segment going to spin out? I can't show you, I can't keep it in the picture, but can you imagine it? The top part here, for example, the point that's on the blue curve y equals x, it spins around a circle. I'm rotating it around the x-axis, circle of radius x. The bottom one spins around a circle. Those circles have the same center. All right, so I have to scroll or a little bit to make room to do this, but if you think about what shape we're going to see, it's going to be the region in between two circles, and those two circles are special. They're so-called concentric circles. They have the same center. So that little region is going to sweep out something. Pretend that I just drew those things with the same center that looks like this. It's not a disc, but people call it a washer, like something that you put on a bolt before you fasten a nut on it, tighten it down. So a washer, or an annulus in mathematics, or the region between two concentric circles. And what's the area of that washer? Well, again, I think we should just think in terms of the difference. This washer at x, its outer radius is x itself. Yeah, it's x itself because it's on the graph of y equals x, and its inner radius, using the same colors, was x squared. Between 0 and 1, x squared is less than that. So the area of this thing, the area at x is, well, you have to take pi times a circle of radius x and subtract pi times a circle of radius x squared. And if you factor out a pi, this is going to be starting to look familiar, I think. That's exactly the function that we integrated to compute this volume. All right. So this sort of example has led us to what we're going to call a sort of different method. If the region, like this region R that you're trying to find the volume of the solid formed by it, if the region is not bounded by the axis of rotation, then your local estimates are not disks, they're disks with holes in them. They're washers, right? And a washer has what we're going to be calling an outer radius. It's the radius of the larger circle, and an inner radius. Yeah, and the idea is that if you want to find the cross-sectional area, you take pi and you multiply it by the outer radius squared minus the inner radius squared. Integrating that from A to B will give you the volume of the resulting solid. Let's summarize that. Here's kind of a general picture of it. You have two functions. I'm going to use highlighting in the same kind of way that I was doing colors above there. So I've got a function f of x. It's an outer function. It's further from the axis of rotation. And then I've got a function g of x, an inner function. It's closer to the axis of rotation. And if I take an x value between a and b in that region R, that line segment that intersects R with points equal to x is going to sweep out a washer. It's going to sweep out a washer. And the area of that washer is, you subtract the area of the inner circle from the area of the outer circle. So your A of x for this setup is given by pi times the outer radius squared minus the inner radius squared. And then that same old principle from the very beginning of the lecture, if you integrate the cross-sectional area formula, you get volume. So this method, people call it integral of solids of revolution by washers. And it's a washer because the local estimate has a hole in it. The local estimate is a washer, not a disk. Let's practice. Going back to that same region, which you might think like, well, wait a minute, we already did this one. Let's practice with something that we haven't already done. This video is getting a little long, so I'm going to make this the last example. But notice that I'm not asking to find the volume around the x-axis. I want to go around the y-axis. Okay, I want to go around the y-axis and find the volume. But we can use the same kind of principles. This time our local estimate, well, a little segment that's perpendicular to the y-axis, so it's going to spin around it, is a segment like that. It still forms a washer. It still forms a washer. It's still got an inner and outer radius, but we're going to have to integrate dy. We're going to have to integrate dy because the washer is determined by a y value, not an x value. Yeah, a y value between what and what? Well, this is actually the point 1, comma 1. So y is also going between 0 and 1. We have to convert these formulas. We have to understand x as a function of y. I have to solve both of these equations for x. That one wasn't that bad. To solve this equation for x, I have to take a square root. I'm taking the positive square root by the context of the problem. Here, y is not a negative number. So when I take that square root, I'm ignoring the negative one. Okay, and now I can see in my picture, the axis of rotation is further away from this value, right? This is the further point away from the axis of rotation. It's on the red curve, not the blue curve. So my outer radius, pardon me, is the square root of y. My inner radius is just y. So the principle that we have to use, the volume is pi. It's built into the formula. The extreme values of y are 0 to 1. And then we have to take outer radius squared. I'm going to write this. I can change the colors here in a second if you want. Minus inner radius squared. Yeah, and do the colors make sense? Well, you're saying they're not colored yet, but the outer radius is the red one. The inner radius is the blue one. It's closer, the inner radius is closer to the axis of rotation. That's how I decide which one's inner and outer. And I have to integrate that dy. All right, so we'll finish this video by just calculating the answer. I won't leave it as a cliffhanger, and I don't have it pre-worked out. So here, well, the square root of y squared is just y. So the antiderivative of that is 1/2 y squared. The antiderivative of y cubed, we've already done it in this lecture. So we have to take pi times 1/2 minus 1/3. Take away 0, the lower limit will be 0, using the fundamental theorem of calculus. And 1/2 minus 1/3 is a sixth. So the exact value of that volume is 1/6. Okay, we'll practice this some more in the next one. I'm going to stop this now. This video is pretty long. Thanks for listening.